Welcome, my dear student. Myself, A. Venkatesan, Assistant Professor, Department of Mathematics, St. Joseph College of Arts and Science, Autonomous, Kadalur. In this video, we're going to learn complex analysis. In complex analysis, first one, we're going to see what is complex plane, sums and product of complex number, and basic properties of complex number. In elementary level, we know what is complex number. So what is complex number? We can write any number z equal to x plus iy, and x and y are real numbers, and we call x is a real number part and y is an imaginary part. Here the same one can be defined as in ordered pair, like x comma y, the Cartesian coordinate form x comma y, where x and y are the real numbers. So to represent a complex number x comma y in a plane, we call it as a complex plane or organ plane or z plane. Any complex plane, x-axis known as real axis and y-axis is called as imaginary axis. If the number is real, then it can be expressed as the ordered pair x comma 0. If it is purely imaginary, it is denoted as the ordered pair 0 comma y. Usually the complex number is denoted as z equal to the ordered pair of x comma y, and we know that x is represented as real part of z and y is represented as imaginary part of z. If you want to say any two complex numbers are equal, the real part of the first complex number and second complex number are equal, and the imaginary part of the first complex number and second complex numbers are equal. Now we're going to see the sum of two complex number. If z1 equal to x1 comma y1 and z equal to x2 comma y2, the sum of two complex number z1 plus z2 is defined as z1 plus z2 equal to x1 comma y1 plus x2 comma y2. So now we add the real part separately and imaginary part separately. Then that will give a x1 plus x2 comma y1 plus y2. Similarly, we can subtract any two complex number. Next one, the product of two complex number. If z1 equal to x1 plus iy1 and z equal to x2 plus iy2, then the product z1 z2 equal to x1 x2 minus y1 y2 comma x1 y2 plus y1 x2. Any complex number z can be expressed as the ordered pair x comma 0 plus the ordered pair y comma 0, or z equal to the ordered pair x comma 0 plus ordered pair 0 comma 1 into the ordered pair y comma 0. So using this way, we can find the value of I square. So using this way, the ordered pair I can be defined as I is a imaginary part. So therefore we can write I equal to 0 comma 1. So I square is equal to I into I. So that is equal to 0 comma 1 into 0 comma 1. So using the product of the complex number, we apply. So we get the value minus 1 comma 0. So as in a real number, that z into any not 0 value, so that is obviously equal to 0. Next one, now we're going to see the basic algebraic properties of complex number. So various properties of complex number are same as the real numbers. So first we're going to see commutative law of addition. So first, what is commutative law? z1 plus z2 equal to z2 plus z1. So that is the commutative law for addition. So now we're going to prove in a complex number. So let z1 equal to x1 comma y1 and z2 equal to x2 comma y2. So z1 plus z2, that is already we know sum of any two complex number is again a complex number. So therefore z1 plus z2 equal to x1 plus x2 comma y1 plus y2. So this now we interchange the addition, that is x1 plus x2 has replaced x2 plus x1 comma y2 plus y1, and this is equal to, we group each one x2 comma y2 plus x1 comma y1, so that is equal to z2 plus z1. Next one, the commutative law for multiplication. So z1 into z2 equal to z2 into z1. Similarly, we take any two complex number z1 and z2. So we are multiplying these two, z1 z2 equal to ordered by x1 comma y1 into ordered by x2 comma y2. So we apply the multiplicative law, so the multiplication of any two complex number, that is, so it gives x1 comma x2 minus y1 y2 comma x1 y1 y2 plus y1 x2. Similarly, we find RHS value z2 into z1. So again it will give the same result. So therefore that commutative law for multiplication in a complex number is also true. Next one, associative law for addition. So now we take three complex number z1, z2 and z3. We apply sum of two complex number form and we going to prove it is also true. So like that we take z1 plus z2 plus z3, that is we take one group z1 plus z2 is one of the group and z3 is separate one, and we know sum of two complex number is again a complex number, and it is also we can write that x1 plus x2 comma y1 plus y2, and third one is x3 comma y3. So now the first part and second part we take real parts, x1 plus x2 plus x3 and y1 plus y2 plus y3. We know x1, y, x2, x3 are real numbers, y1, y2, y3 are real numbers. In a basic information, real numbers are satisfied the associative. So therefore we rearrange the group. So x1 plus x2 plus x3, it is one group. Similarly, in the imaginary number, imaginary part, that y is also real number but imaginary part, we group y2 plus y3 is one group. So again it will gives that x1 comma y1 plus x2 plus x3 comma y2 plus y3. So that is equal to z1 plus z2 plus z3. The next one, associative law for multiplication. So again we take three complex number z1, z2 and z3. So now we find the first one z2 and z3, we multiply two complex number, we will get x2 x3 minus y2 y3 comma x2 y3 plus y2 x3, and we multiply these result into z1, that is ordered pair x1 comma y1 to the ordered pair x2 x3 minus y2 y3 comma x2 y3 plus y2 x3. So now we apply again the multiplication of any two complex number. So we'll get the result as x1 x2 x3 minus x1 y2 y3 minus y1 x2 y3 minus x3 y1 y2 comma x1 x2 y3 plus x1 y2 x3 plus y1 x2 x3 minus y1 y2 y3. Similarly, the RHS z1 and z2, by using the multiplication of any two complex number, we get the result is x1 x2 minus y1 y2 comma x1 y2 plus y1 x2. So now we take, this is a single complex number, so now we multiply that z1 z2 into another one complex number z3. So again we multiply multiplication of any two complex number, so we get the result is x1 x2 x3 minus y1 y2 x3 minus x1 y2 y3 minus y1 y2 x2 comma x1 x2 y3 comma y1 y2 y3 plus x1 y2 x3 plus x2 x3 y1. So now we compare equation 1 and 2. So these are equal. So therefore z1 into z2 z3 equal to z1 z2 into z3. Next one, distributive property. z1 into z2 plus z3 equal to z1 z2 plus z1 z3. In LHS, we add two complex number and we multiply with the one complex number. So we take three complex number z1 z2 z3. So z1 into z2 plus z3 can be written as that ordered pair x1 comma y1 into sum of two complex number. So that is x2 plus x3 comma y2 plus y3. Again, we apply multiplication of two complex number. So that is x1 into x2 plus x3 minus y1 into y2 plus y3 comma x1 into y2 plus y3 plus y1 into x2 plus x3. So this gives x1 x2 plus x1 x3 minus y1 y2 minus y1 y3 comma x1 y2 plus x1 y3 plus y1 x2 plus y1 x3. Similarly, we find RHS value and z1 z2, that is we multiply the two complex number z1 z2, we get one result, we call it as equation number 2, and z1 z3 and we call it as equation number 3. Now we add these two equation and this gives the equation number 1. So from 1 and 2, the distributive law for any complex number is satisfied. Additive identity. What is identity? Any number z, we can add whatever the number, we can get the value z. So like that, additive identity of complex number is 0, 0. So since we add z plus 0 or 0 plus z equal to z. So ordered pair x comma y plus 0 0 equal to the ordered pair 0 0 plus ordered pair x comma y equal to again the ordered pair x comma y. Similarly, multiplicative identity for the complex number is 1 0. The ordered pair x comma y into ordered pair 1 0 equal to ordered pair 1 0 into ordered pair x comma y equal to ordered pair x comma y. So that is we using the multiplication of any two complex number. So what is multiplication of any two complex number? z1 into z2 equal to x1 x2 minus y1 y2 comma x1 y2 plus y1 x2. So like that here 1 into x equal to x minus 0 into y 0. So we get the real part is x and imaginary part is 1 into y plus 0 into x is 0. So y plus 0 again y. So therefore we get the ordered pair x comma y. So the multiplicative identity and additive identity of any two complex number is satisfied. So next one is the additive inverse of the complex number. So what is inverse? Any number is there exists a number is a dash. We are adding these two, we get the value identity. So that is the concept of additive inverse. So like that, we are taking the complex number x comma y and the additive inverse of complex number is we choose x dash comma y dash. So we are adding these two by the law equal to 0, 0 or the x dash comma y dash plus x comma y equal to 0, 0. So now the addition of any two complex number, we know again it is a complex number. So therefore we add these two ordered pair. So x plus x dash comma y plus y dash equal to x comma y 0, 0. So this gives real part equating the real and imaginary part. So it will give that x plus x dash equal to 0 and y plus y dash equal to 0. So which gives x dash equal to minus x and y dash equal to minus y. So that is additive inverse of z is minus z. Multiplicative inverse of z. A non-zero complex number z as inverse with respect to the multiplication is defined as x comma y into u comma v equal to 1 comma 0, or u comma v into x comma y is also equal to 0. By using the multiplication of any two complex number, we get the value xu minus yv comma xv plus yu equal to 1 comma 0. Now we equating real and imaginary part, we get xu minus yv equal to 1 and xv plus yu equal to 0. So these are the algebraic equation form. So we simplify this equation, we get the value for u and v, so that u and v are the multiplicative inverse of z. So therefore the multiplicative inverse of z is x by x square plus y square comma minus y by x square plus y square. And the remaining property will be seen in the next classes. Thank you.